Hello, good morning, good evening. I'm audible to you. खाना खा लो जाओ. Okay, I'm audible to you, Mr. Kartis Chiru. So, in the last lecture, we have completed the topic conduction. Now, today we are going to start the convection. The It's a third chapter. First chapter was introduction, and in that first lecture, I told you the basic about the conduction, convection, and radiation, all three modes. Now, in the second chapter, we just specifically start the conduction that we have completed so far. Now we are going to start the third chapter, which is convection. Clear? Okay. Any doubt to anyone? Up to this lecture, is there any doubt? In any question that I have given as assignments, so are you solving the questions from the sources that I told you, Mr. Karthis? If you have any doubt regarding any questions based on the topic conduction, please ask me. I am ready to discuss. Prachi, are you there? Okay, we are going to start the topic here, convection. So thus far we have focused on the heat transfer by conduction, and we have covered the topic convection only to the extent uh, for the introduction point of view. Only we have discussed the convection in the first chapter for the introduction point of view. But now in this chapter we are going to start in detail about the convection. If you recall, I told you the convection is not a phenomena. Convection is simply conduction along with the bulk motion. है ना? If the molecular heat transfer is via conduction, if molecular phenomena is going to be assisted by the bulk motion, that's called as convection. So convection is not the word convection is not restricted for the heat transfer. Even we can use in the mass transfer, and also we can use in the momentum transfer. So as far as the significance of convection in the heat transfer is concerned, our general definition of convection is nothing, it's simply called as molecular diffusion of heat plus bulk motion. So whenever molecular phenomena is going to be assisted due to bulk motion, that's called as convection. So in the heat transfer we are going to talk about molecular diffusion of heat. So if the heat diffuses or heat transfer through molecular phenomena, that called conduction, is going to be assist or support or aid by the bulk motion, that's called as convection. In short, I told you convection is nothing, it's called as conduction plus advection. Clear? And as I told you, convection heat transfer does not takes place in the Mr. Devendra. It doesn't takes place in the solids. It always takes place in the fluid between the surface of the solids and the fluid flowing over it. That's called convection. That basic things already I told you. Right? If you have gone through the lectures of the lecture first, then you got clarity about the convection. And I told you, whenever I am talking about convection, the boundary layer is very important. The concept of boundary layer is central to understanding the convection heat and mass transfer between the surface and a fluid flowing past it. And why the boundary layer is important? Because I told you, whenever most of the cases, convection heat transfer, in most of the cases, convection heat transfer taking place between the solid surface and fluid flowing past over it. Yes or no? So whenever for example of convection is just I told you कि if you have a hot boiled egg or any hot object you place in the environment, then from surface of solid to the fluid, heat transfer is by convection. Yes or no? Same thing we have seen in the fins. In the fin, when a fin we have attached, then from the surface to the surrounding fluid, the heat transfer is by convection. Although we have already discussed the convection phenomena in the fins and all, but here in this chapter we are going to focus how we can enhance the heat transfer coefficient and how the heat transfer coefficient is associated with the convection heat transfer. These all things we'll discuss here. So as far as convection chapter is concerned, or convection heat transfer and convection mass transfer, because I told you the convection chapter is, the convection word is not restricted for the only heat transfer, it can also use for the mass transfer, because the meaning of convection, the definition of convection is nothing, it's called as molecular diffusion and collision plus bulk motion. Is this clear? Molecular diffusion of the molecules plus what? I told you, if you recall the lecture, plus advection. This is called as convection. Mr. Karthis. Yes, bulk motion means advection. So as far as convection heat transfer is concerned, it depends upon the various parameter. I told you it's a very complex mode of heat transfer. Why it's very more complex? Because this mode of heat transfer is strongly influenced by the flow field. So as far as definition is concerned, the convection heat transfer, I told you definition in the starting, I will not write here. So only I will write the main important points. The rate of heat transfer, definition I told you, the rate of convective heat transfer is strongly influenced by flow field and flow profile, flow field and flow velocity, and also the fluid properties. it is a very complex mode of heat transfer. Why? Because its rate depends on various parameter like the rate of heat transfer will depend upon the various parameters like delta T is what temperature difference, area, you know Q H A delta T है ना, तो delta T area, and along with this the density, velocity, specific capacity. So these all weightage that you said here, U and rho nu Cp K है ना, so these all the fluid properties, yes or no, along with this Lc also. So what you are going to see here, this combinedly is involved in the function of H. So you can say that's why the Q dot equal to what, H A into delta T. It's called Newton's law of cooling. Newton's law of cooling, yes or no? I told you. So although the expression for the calculation of heat transfer coefficient, heat transfer rate by convection is very simple. H A delta T. H is the heat transfer coefficient between surface and fluid. Past it. A is the area for the heat transfer. And this is what temperature difference is, Ts minus T infinite. Surface temperature minus surrounding fluid temperature. Is this clear, beta? So although it is a very complex, but still it is a very simple expression to find the rate of heat transfer by convection. Now all the complexities involved in calculation of heat transfer coefficient, all complexities, because if H is known to you then it's very simple, but all the complexities to find the value of H. How can find the H value of H? All complexities of convection heat transfer is in calculation of heat transfer coefficient. All the complexities of convection heat transfer is in calculation of heat transfer coefficient, as H heat transfer coefficient depend upon the number of parameters like density, viscosity, Cp, thermal conductivity, velocity, and Lc, which is called characteristic length. This is called as thermophysical properties of the fluid. This is called as thermophysical properties. Sorry, except for the U. U is the velocity, Lc is the characteristic length. Clear? So this is, even this value of H is for the heat transfer, convection heat transfer that does not involve phase change. Clear? If we are talking about convection heat transfer involving phase change operation like boiling and condensation, then it is very much more complex. Is it clear, Mr. Devendra? Already I told you, if you go for the introduction lab chapter of the convection, I clear many things about this. No, listen, right? For convection heat transfer, for convection heat transfer involving phase change operation, like boiling and condensation, because they are the example of convection heat transfer that involve phase change, where the phase will change. And in that case, in this case, H depends on following parameters or variables. Along with this, density, viscosity, Cp, K. Along with this, it also depends upon surface tension, lambda. Okay? U and Lc. So two additional parameters that will be added when talking about the heat transfer involving phase change. So what you are saying here, dependency of heat transfer coefficient on the parameter will get increases. So obviously that H depends upon the number of parameters. Although H is not a property, but it depends upon the property of the fluid. So you should not say that H is a property. No, it is simply terms which depends upon the property of the fluid and various parameter. So that's why you can see the variation of H with number of parameters. So question is that how can you find their dependency on various parameters? It's very difficult. Yes or no? So if listen, for the given, this is for the phase change operation, and that dependency of heat transfer coefficient for the heat transfer convection heat transfer problem that does not involve phase change. This is for the convective heat transfer operations that does not involve phase change, just like cooling and heating of any object. But if you're talking about convection heat transfer involving phase change, then the sigma, which is called as surface tension, and this is the latent heat of phase change that will come into picture. Clear, beta? So first I will in this chapter we are going to discuss the convection heat transfer that does not involve phase change. So if that does not involve phase change, then obviously for convection problem that does not involve phase change or without phase change, heat transfer coefficient depend upon the density, viscosity, Cp, thermal conductivity, velocity and characteristic length. I told you. So obviously if you see, it's very difficult to find the relationship between the heat transfer coefficient and number of parameters, because there are very large number of parameters are there. So if property of the fluid is same, if the fluid is same, then density same, mu same, Cp same, K same, K is thermal conductivity. Now then the heat transfer coefficient depend upon the velocity and Lc, and the velocity will strongly depend upon the types of flow field. Clear? Which types of flow, laminar flow, turbulent flow, which types of flow conditions are there. So that's why I told you this convection heat transfer is strongly influenced by the flow field or flow velocity. Which types of fields are there, laminar flow field or turbulent flow field, which types of flow fields are there, depending upon that the heat transfer coefficient will depend for the given fluid. Clear? What does it means here? For example, if suppose you have a hot boiled egg, if you want to cool, same air is there without any bulk motion, stagnant air, another is air with some velocity. It is clear? The air is same means fluid is same. The same air, one times we have placed the same hot boiled egg under stagnant air, and other times in other hot boiled egg we place in the flowing air. So what is the difference in these two? Is the property of fluid has been changed? No, property of fluids are same because both are air, but the flow condition has been changed. In one case the fluid was stagnant, and other the fluid is moving. Clear? Is this clear? So this is how the velocity of the fluid will affect the, I told you just for you are taking a samosa, you are eating a samosa, then what happen? If samosa is very hot, then you use the blow air from your mouth. If you are blowing air through mouth, then obviously it will cool fast and you can consume it as early as possible. But if suppose someone is not blowing, then it allowed to cool naturally, है ना, then obviously it will take much longer time to cool it. So in both cases the rate of heat transfer by convection is different. Rate of heat transfer, both are convection phenomena, but their rate is different because of what is difference in these two cases? Only the value of H has been changed. H depends upon the flow conditions. All the property of fluid is same air is there, but you have, by blowing the air through your mouth, you are increasing the velocity, and that causes the high value of H. So depending upon the bulk motion, I told you ki the flow velocity or flow profile, है ना? So that's why I told you this mode of heat transfer strongly influences the flow field. That's why two types of convection problem is there. One is forced convection, other free convection. So what is forced convection? In the force, this is for the forced convection. Whenever velocity is coming into picture, that's called a forced convection. So if you go from the much more basics, then convection heat transfer operation, I told you it's a transfer of the energy between the surface of the solids and fluid flow past it. Okay, and as far as convection is there are two types of convection depending upon the types of bulk motion, okay, through which we have induced the bulk motion. So depending upon the mechanism of bulk motion induced, mechanism of induced means how we have induced the bulk motion in the fluid, the two types of convection is there. One is called as natural and force, clear. Another classification is depending upon the phase involved or not. If it does not involve phase change, that's why convection heat transfer without phase change, and if it involves phase change, called as convection heat transfer with phase change, like boiling and condensation. That I already discussed, I will not write here. So now you can see here the depending upon mechanism of bulk motion, induced in fluid, there are two types of convection. One is called as forced and other is called as free or natural convection. So basically we have written the all things for the forced convection. In the forced convection, the bulk motion induced due to external sources. Here bulk motion is due to external agencies like pump, compressor, fans, blowers, etc., etc. So these are the sources of the bulk motion. Now in the free convection, it's because of difference in density which has been caused by difference in temperature. I told you, no? So it's due to buoyancy effect which has been. So in natural convection, the fluid motion induced due to buoyancy effect which has been caused by difference in density due to difference in temperature. Clear? Due to buoyancy effect. And what is the reason for buoyancy effect? Difference in density. And why difference in density has been rise? Because of difference in temperature. Is this clear? So indirectly you can say because of difference in temperature there is a difference in density which induce a buoyancy force, and that causes the bulk motion in the fluid. So in the free or natural convection, the bulk motion induced is because of natural phenomena, that is difference in density. caused by difference in temperature. But in the forced convection, we induce the bulk motion by the external sources, pump, blowers, compressor, fans, etc. That's called as forced convection. Clear? And as far as property of the fluid is same here, only the thing which is changed is the velocity. Huh? So in which mechanism of the bulk motion the fluid velocity is higher? Obviously in the forced convection. In the forced convection, the velocity of the fluid in the bulk motion, velocity of the fluid is much higher than 1 meter per second, while in the free convection or natural convection, the velocity in the fluid which arises due to difference in density is less than 1 meter per second. That's why the heat transfer phenomena by forced convection is much higher than the free convection. Clear hai beta? So this is I written for the forced convection. This is the forced convection problem. Please write all are the forced convection. When we come to natural convection, then the velocity will not come into picture. Then the term that is beta come into picture. Beta is called as volume thermal expansivity, that I will discuss. Clear? So we are specifically going to start the forced convection. Clear? So this is the first classification of convection problem depending upon the mechanism of bulk motion induced in the fluid. It's the first classification. Second classification is of the convection heat transfer operation is based on the phase change involved. Based on phase change involved. The two types. One is convection without phase change. Without phase change, and second is convection with phase change. Convection heat transfer with phase change. Clear? And other is depending upon the types of flow, internal or external, है ना? Based on types of flow. The two types is there: external forced convection, external forced, and internal forced. Clear? So basically now the first topic that we are going to start is the convection heat transfer, or we are going to start external forced convection heat transfer without phase change. Clear? Means external forced convection means what? Means in which the fluid is allowed to flow over the, here fluid flows past solid surface. For example, flow over flat plate, flow past flat plate. Second example, flow past sphere or cylinder. Clear? They are external force convection. As far as internal force convection is that fluid flows within a confined boundary. Fluid flows within confined boundary. For example, flow of fluid within in circular channel. Flow of fluid between parallel plates. Parallel plates, etc. है ना. These are the internal force convection. Is it clear बेटा? तो all the topics are clear. So first we are going to start here the next convection heat transfer of force convection first. So what if in the force convection, which case, external or internal? We are talking about external. Now the topic is external force convection. External force convection without phase change. Clear beta? So external means the fluid flows past the solid surface. Force means the motion, bulk motion in the fluid induced by the mechanism of external agencies like pumps, compressor, blowers, etc. Without phase change means it's simply cooling and heating. There is no phase change involved. Clear? So in this case, I told you the heat transfer is dependent upon its HA into delta T, where H is depends upon rho, and now we are going to be specific here. Rho, mu, Cp, K, all property of the fluid is there. Along with the fluid, that is called as U infinite. What is U infinite? I will discuss. What is here LC? Its characteristic length. So U infinite called as here the upstream velocity. Upstream. Clear? And their properties, it's called as upstream velocity. Clear beta? Bolo. So as I told you कि all the complexities of the convection heat transfer only involved in the calculation of H. How we are going to find the H? Obviously we should do the experiment, है ना? Because if you are going to carry out the experiment, that you know कि that is very difficult because there are very large number of parameters. It's not only one or two parameters. There are 6 parameters are there in total. And one by one we have to change the parameter, keeping all other parameters constant. Then we are able to know कि how the H. For example, suppose you want to find out how the density will affect the heat transfer coefficient. Then what you should do? You should fix the mu, Cp, K, and U infinity and LC. All other parameters should be constant. You should fix, and then you will change the value of rho, and then we will find how the H will vary with the rho. But the problem is that sometimes as the rho will change, as the density will vary with temperature, and viscosity is also function of temperature, then both will vary. Both cannot be constant at the same time. Is this clear? That is the problem here. So one very simple technique is there. It's dimensional analysis method. Via dimensional analysis method, we can reduce the number of parameters into small dimensionless numbers. I think I told you in the starting lecture. So by using dimensional analysis method, we can reduce the number of variables by grouping it into dimensionless numbers. Dimensionless numbers. Huh? So this is what the two method. One is called as method which is used to reduce the number of variables by grouping into dimensionless number is called as Buckingham Pi method and Rayleigh method. That you know, Buckingham Pi method and Rayleigh method. So what I will do here, by if I will use here, then I will got here Nusselt number as a function of Reynolds number and Prandtl number that I got here. Clear? Where Nusselt number, Nu is the Nusselt number, R is Reynolds number, and Prandtl number is PR is Prandtl number. Now, but again the problem is that what is the functional dependency of the Nusselt number and Reynolds number and Prandtl number? For this we should now carry out the experiment. Now it is very easy to carry out the experiment. Why? Instead of observing the effect of 6 parameter on the heat transfer coefficient, now it is very easy to observe the effect of 2 parameters on the Nusselt number. Clear? Now what we will change, instead of changing the density and velocity separately, we will change simply Reynolds number. Is this clear? So now by carrying out the experiment, here Nusselt number is equal to, let's say, C into Re ki power m into Pr ki power n, where C, m, n are the constants, and this constant we can only get from the experiment, because they are the functional dependency of how the Nusselt number, because this function na, so what function is there that we don't know, that totally depend upon the experiment. C, m, and n are found from experiment. Clear? Tell me please. Clear Chiru? Sambit, Kartis, Abhishek, Devendra, Palak. So in this case what we should do, it's if you are going to carry out the experiment, then simple, I will show you in the later upcoming lecture ki how can perform the experiment. We just fix the value of I will discuss ki how can find this functional dependency later on, but that is a way. Is this clear? And what the Nusselt number, what the Reynolds number, what Prandtl number, what their significance, that all will discuss in the upcoming lecture. But before this, what the important thing is that ki this heat transfer coefficient, or indirectly you can say Nusselt number, will strongly influenced by the Reynolds number. And Reynolds number will depend upon the types of flow conditions, laminar flow and turbulent flow. Huh? And that's why you can say the indirectly you can say, as I told you, U infinite, or you can say U here, because we are talking about external force convection. Clear? Now, so why the boundary layer why the boundary layer will play important role in the convection heat transfer? Is this clear? Because boundary layer uh, thickness, all the resistance, why the boundary layer come into picture? Because suppose I'm talking about the external flow. Let's say this is what the flat plate is there. Try to understand here. And if the fluid is going to flow here, then obviously all the resistance for the heat transfer will confined within the small boundary layer thickness. Outside the boundary layer, there is no gradient is there. So all the resistance is confined only a small region close to surface. That's called as boundary layer. Is this clear? So question sometimes in the interview they used to ask why the boundary layer is important. So you should say, okay, sir, actually all the resistance for the heat transfer or mass transfer will lies or confined only a small region close to the surface boundary. So instead of worrying about the other region, we should only focus on the region which are close to the boundary of the solid. That's called as boundary layer. It is similar to the film theory in the mass transfer. Because what the Whitman has been assumed कि all the resistance for the mass transfer lies only in small film stagnant, a small film close to surface which is stagnant. है ना? So the same thing here कि if any fluid flows over the surface causing the heat transfer, mass transfer and momentum transfer, so for the heat transfer, mass transfer, momentum transfer, the gradient, for the heat transfer the gradient is temperature gradient, for the mass transfer the gradient is concentration gradient, and for the momentum transfer gradient is velocity gradient. You know, these all the gradients for the mass transfer, momentum transfer and heat transfer lies a small film of the fluid close to the surface boundary. So only we should focus on that film instead of bothering about the infinite film. Is this clear? That's why the boundary layer is important in the study of convection heat transfer. Is this clear? Bolo. So you should write importance of boundary layer. Heading is importance of boundary layer. So what is it कि as fluid flows past solid surfaces, all the gradients it means temperature gradient, for heat transfer, concentration gradient for mass transfer, and velocity gradient for momentum transfer. Confined bracket closed, all the gradients confined close to surface boundary, hence called boundary layer. Hence it's play very important role, very important role in convection problem. In convection problems, ठीक है, convection problem is the phenomena that involve bulk molecular motion as well as the bulk motion. Clear? Molecular diffusion and bulk motion, that's the convection problem. So first boundary layer that I am going to discuss here is the velocity boundary layer. Is this clear? There are following two boundary layers are in convection heat transfer. One is called as velocity boundary layer, another is thermal boundary layer. Clear है बेटा? बोलो. Velocity boundary layer and thermal boundary layer. First I am going to discuss velocity boundary layer. The velocity boundary layer. कोई problem? Everything is going to be in sequence. The first we are going to discuss here velocity boundary layer. पलक कोई प्रॉब्लम? पलक देवेंद्र now as far as velocity boundary layer is concerned, as the fluid allowed to pass, as suppose for example if the fluid flows over the surface of solid, for example your table is there na, and air is flowing over it, so just you can imagine this is what the flat surfaces, this is what the leading is, means starting is, leading edge of the plate. It's simply front view of a table. Top view will be like this plan, and the fluid flows over it with the velocity up, stream velocity u infinite. The fluid flows, fluid may be any fluid, air or anything, it's y direction, it's x. So fluid flowing with the velocity of u infinite, which is called as upstream velocity of the fluid. As the fluid come into contact with the surface, as a plate is there. Clear? Now here its length is L. Clear? Can you imagine? A plate is there, just you can assume your table, and fluid flows with the velocity of u infinite. Clear? Their density rho and viscosity and all are property of the fluid. Now as the fluid flows over it, what happens? when the fluid particles make contact with the surface, what happen? Their velocity come to zero, their velocity reduce significantly, and velocity of the fluid become zero at the wall. As fluid, listen once again, as the fluid particles make contact with the surface of solid, the velocity is reduced significantly with respect to the fluid velocity upstream of the plate. With respect to upstream velocity of the plate, the velocity of the fluid which are close to surface, which make contact with the surface, will be very small, and it becomes zero when the fluid is just on the surface. Yes or no? And this is what called no slip condition, because no slip condition means particles of the fluid does not roll over the with respect to surface. If surface is stationary, then particles of the fluid will also be stationary. Is this clear? So what happened here, just try to imagine, if suppose if a fluid is going to flow over your table, just your table is there and fluid allows to flow with the velocity of upstream velocity u infinite. Uniform velocity were there. Here at before x equal to 0, the velocity were uniform. You can see uniform velocity is there. Clear? This indicates you uniform velocity. At all y, the velocity is uniform. But as it come into the contact with the surface of solid, means any fluid particles which comes to the contact with the surface of solids, their velocity will reduce significantly with respect to the velocity of upstream, and its velocity becomes zero when the fluid particle is just on the surface. And these particles then act to retard the motion of particles in adjoining fluid layer. Yes or no? Because I told you any fluid particle just on surface will have zero velocity, and this velocity, or you can say any particles of fluid which are close to surface, will have very small velocity, and that velocity, that particles of the fluid will act to retard the motion of particles in adjoining layer. Let's say here different layers of the fluids are there. There are different layers of fluid are flowing. The first layer, which is just on surface, will have zero velocity. Any layer above this will have some velocity, but its velocity is very small as compared to upstream velocity. So when the velocity of the fluid particles reduce significantly and become zero at the wall, that particles acts to retard the motion of the particles in adjoining fluid layer, and which acts to retard the motion of particles in the next layer, and so on until a distance y equal to delta, where the effects of change in the velocity become zero. Is this clear? Suppose this is what the plate is there. You can imagine, if I'm talking about any distance here on the plate, the velocity at the surface is become zero, and that as we are going to move here, its velocity get increases like this. You can imagine it's a plate is there. It's a plate. You can make a plate. As the fluid become here, the velocity of the fluid at its y, at y equal to 0, velocity is 0, and as we moving away from the surface, the velocity get increases. You can see here the velocity get increases, and I told you why the velocity close surface has been reduced, because of, I told you, any fluid layer, when the fluid particles come into contact with the surface, their velocity is reduced significantly with respect to the velocity of the upstream of the plate. And for the most distribution, it is valid to assume the particles velocity is zero at the wall, no slip condition, and these particles then act to retard the motion of particles in the adjoining fluid layer, and which acts to retard the motion of the particles in the next layer, and that goes so on until a distance y. This till a distance y equal delta. This is what y equal to delta. from surface where the effect of the surface is negligible. The velocity of the fluid is means what I'm saying to you, the resistance or you can say the effect of surface on the fluid particles is only up to distance y equal delta. Beyond that distance the fluids moving without any reduction, without any change in the velocity. You can see here. Is this clear, beta? So only delta is the important for our consideration for study point of view. Why? Because no resistance beyond that. All the resistance is only up to delta. Because all the gradient in the velocity is from here. The velocity is what delta is there, where velocity is close to or 99% of upstream velocity. Is this clear? This is the thickness is called as boundary layer thickness. Ready? Clear? So as I told you ki velocity has been here u equal to 0 and 0 to nearly upstream velocity we are getting only in the delta thickness of the film in the y direction. So most of the velocity, most of the gradient lies in only that here. Beyond that there is no change in the velocity. Velocity is uniform here. You can see uniform with the velocity of u infinite. So it means all the change in the gradient or gradient will exist only in the smaller region close to surface, and that's called boundary layer region. Clear, beta? The fluid, all the fluid is flowing throughout, but only the smaller thickness close to surface which are influenced by the flow field or which are influenced by the surface boundary is called boundary layer thickness or boundary layer region. Clear hai? Yes or no? Clear hai? Yes or no? Now, so listen, as we have seen here, du upon dy means change in the velocity. This is the length will indicate you the magnitude of the velocity. A smaller length here, a smaller velocity, and this is y here, means the gradient is there only up to boundary layer thickness delta. And what you have seen here, the retardation of the fluid motion, because fluid motion has been retarded now. So this retardation of the fluid motion is associated with the shear stress. Why? Because shear stress is what? What is the reason for shear stress to develop? Now the term is called as shear stress. Shear stress. What is shear? Shear means, do you know what is shear? Shear means shear means a relative displacement. A relative displacement of one with respect to another is called as shear. Clear? For example, if suppose you have two block is there, one block is this and other block is this. If one is moving with the velocity of, let's say one is stationary and other is moving, then there means the upper layer have a displacement over the with respect to the bottom layer is called as shear. Is this clear? What do you call as stress? Stress is nothing, it's a force upon area. But what is shear stress? The force which causes the shear, the force acting per unit area that causes shear, or a relative displacement is called as shear stress. Is this clear? The force acting per unit area is called as force upon area is called as stress. Clear? So what is shear stress? The force which are acting per unit area which causes the shear into the fluid, shear into the object is called as shear stress. Means for example, if let's say one block is there and other block is here, and this block is moving with the velocity of 2 meter per second and this is moving with the 3 meter per second, means upper block have a relative velocity of 1 meter per second with respect to the second layer. Yes or no? The force which causing this motion, because we are pulling with some force here, we are applying some force here, this force is called as shear force, and the shear force which are acting on unit area of the object is called as shear stress. Is this clear? And the fluid mechanics we are able to know, it is clear what is shear stress. And in the fluid mechanics that we know very well, shear stress is proportional to rate of deformation. Means I told you कि as you have seen कि there is a, as we move away from the surface, the velocity gets changes here. If I'm talking about two layers of the fluid here, listen, very important here. If I'm talking about any two layers, let's say in a larger manner, I'm going to indicate you. Suppose this is one layer of the fluid and this is any plane between this. Any plane we have considered here, and I just told you कि one layer and other layer here. So as I told you कि the two layer of the fluid is there, you can see the two layer, this we have enlarged here. Here the velocity is u and here u plus du. Clear? And distance is here from the origin, this is what y, and this is y plus dy. dy. So as you move a distance from y to dy, the velocity of the fluid has been changed from u to u plus du. Yes or no? Bolo. From the distance here, it's y is there, na? So from a distance y, the velocity was u. At distance y plus dy, the velocity is u plus du. So how much is the gradient? Gradient means change in the velocity with respect to change in the distance. So the gradient is what here, du upon dy. Means the change in the velocity with respect to y. Is this clear? So if you observe carefully, then what you found here, you found the increase in the velocity is of du and the increase in the distance is by dy. So if you draw a tangent over it, the tangent will give you dy upon du, but gradient is du upon dy. Inverse of this slope is called as gradient. Is this clear? बोलो बेटा देवेंद्र. And that this retardation in the velocity, this retardation in the fluid motion is associated with the, that is associate with the shear stress acting on the planes. And direction of shear stress, because this is the shear stress is nothing a force which causing the displacement, and displacement is it's always parallel to surface. The shear stress tau that is acting in the plane that are parallel to the fluid velocity is tau. So what we have seen here, कि as the fluid particles come into the contact with the surface, the velocity become significantly less as compared to upstream velocity, and it can be assumed to be zero when the fluid particles on the surface. That velocity, that fluid particles acts to retard the motion of the fluid particles as joining the other layer and so on, है ना? And this will continue till delta distance, where the effect of surface, effect of the solid boundary is negligible, or beyond that the gradient is zero. And this retardation of the fluid motion is associated with the gradient of the velocity or causing shear stress, and shear stress proportional to gradient and the velocity. Is this clear? And here u infinity called free stream velocity beta. It's called as free stream. I will discuss what is the difference in the free stream and this is upstream. Upstream and free stream will be equal when there is no pressure gradient. I will discuss it later on, but it's a very important point. Any problem? So first of all, what is the theory? Theory is that I will discuss why we are going to bother about boundary layer, because I told you all the gradients for the heat transfer, mass transfer, and momentum transfer lies in the lies to closed surface, lies in the film which are closed surface, and that's called the boundary layer. So what we have seen here, as we have studied boundary layer, as the fluid pass the surface of solid or flow flat plate, so as the fluid particles come into contact with the surface of solid, that's causing the retardation in the velocity with respect to the velocity of upstream, and these particles tends to or acts to retard the motion of particles in the adjoining fluid layer and which acts to retard the motion of particles in the next layer, and so on until a distance y equal delta from the surface the effects become negligible. Effect of what? Effect of surface boundary. And this reduction of fluid motion is associated with the shear stress, है ना? And shear stress is proportional to gradient, and the proportionality constant is what? Viscosity, that you know very well. In the fluid mechanics I will discuss it. So as also I told you here, you have seen the upper layer and lower layer, and that causes the gradient, and this gradient causing the stress to develop. That due to this gradient in the fluid layer, there is a development of shear stress, and that shear stress proportional to gradient du upon dy, and that tau gradient proportional to mu into du upon dy. Clear? Mu is called as viscosity, and this is called as Newton's law of viscosity. Clear है? बोलो. So as I told you, this gradient only exists up to delta thickness. Up to delta thickness, the gradient. Outside the delta, is there any gradient? No. It means the stress is zero. Means all the gradients, all the resistance for the momentum transfer is lies only in the small hypothetical film, small film that is called as boundary layer thickness. So what is boundary layer? Is this clear? What is velocity boundary layer? Is this clear? Clear? Now the point you should write here, when just I told you, but I'm going to write in words. When fluid particle, when fluid flows over the flat plate, the fluid particle makes contact with the surface. Their velocity is reduced significantly relative to free upstream velocity. Clear? Of plate, and velocity is zero at the surface. Velocity zero at the surface. Clear? So the particles whose velocity is reduced significantly, that acts to retard the motion of adjoining fluid layer. Yes or no? These particles then act to retard the motion of particles in the adjoining fluid layer. Which acts to retard the motion of particles in the next layer. In next layer, है ना, and so on until at a distance y equal to delta from surface, the effect of particles to reduce the velocity of adjoining layer effect becomes negligible. ठीक है, and this retardation of fluid motion is associated with the shear stress tau proportional to du upon dy, and tau is equal to mu into du upon dy. So when there is a gradient in the velocity, that causing the stress. What happened with increasing distance? With increasing distance y from surface, the x component velocity, x component means u, x component velocity क्या हो रहा है of the fluid, increase or decrease? X component velocity must then increase, very good, until कब तक? Until it approaches the free stream. What is free stream? The stream which are free from the surface. Free stream value of u infinite. Clear beta? So how can define delta? Delta is nothing a boundary layer thickness, and it is defined as the value of y for which the velocity is close to 99% of what? Free stream velocity. Clear? Hence we can define the boundary layer thickness. Boundary layer thickness, first of all, physically the region in which the gradient exists, the region of the fluid flow, a fluid motion in which gradient du upon dy exist, called as boundary layer thickness. Yes or no? It's one meaning. Other meaning you can say also, the defined as the value of y, or it is a distance in y direction from surface for which velocity is 99% of free stream velocity. Yes or no? बोलो बेटा. It's called boundary layer thickness. Any problem till point? Tell me. Now, so as here you have seen, is this thickness is same for all length of the plate, or will it change? This thickness I got here, let's say this delta I got here at the distance of x from the leading edge, is the same distance will be same y is there, same boundary thickness is there for all length from the leading edge of the plate, or will it change? Here next one looking at here, with very important thing, with increasing distance, with increasing distance from the leading edge, the effect of viscosity, the effect of viscosity penetrate farther, farth, farther, much more distance into the free stream, and the boundary layer grows. It means delta increases with x. That's what important here. Why it grows, I will discuss it first, right? It means if I'm going to draw the figure here, rough figure, just you can imagine, this is what the uniform velocity, it's called upstream velocity infinite, and this is what the fluid flowing, and this is what called as a boundary layer. Why is? Because if you draw the profile, I got this as a delta 1. Here I got this delta 2. So it's 1 point is 2 point. So from leading edge, its distance is x1. This distance is what? x2. So here delta 1 and delta 2. As you move much farther into the downstream, with increasing distance from the leading edge, x1 to x2, the effect of viscosity penetrates farther into the free stream. At x1 distance, only that much only it means effect of surface boundary is only up to this length, delta 1. But as you move away from surface, much more distance from surface from leading edge, then the effect will be more farther into the free stream. Here delta 2 has been increased, so delta 2 more than delta 1. Why it has been so? Anyone reason can tell me? Why the thickness get increases? Why delta get increases with x? Tell me. Delta is the boundary layer thickness and it is a function of x. As x will change, the thickness will change. Why it get increases? Anyone? Reason is very simple. For example, if you observe, suppose a fluid is flowing here, so at, let's say, from surface, just you can imagine, this is where the surface is there, na? It's for y distance, y. From surface, this distance I'm talking about. This is, let's say, very small distance in the y direction. So at a distance of, let's say, 1 millimeter, the velocity at 1 point and 2 point, which point velocity is more? At 1 millimeter distance from surface. Anyone? At 1 millimeter distance, let's say the plate is there, and this is what the y is axis here, and I have just considered 2 points here, and the fluid is flowing x direction here like this. The velocity at this point and at this point, which point velocity is more? This is 1 point and this is 2 point. Tell me please. At the same distance in the y of 1 millimeter, the velocity of the fluid is higher at 1 point or 2 point. Tell me. Obviously it will be higher. So you can say yes, at 1 point velocity is more, at 2 point velocity is less. It means if u2 velocity at 2 point is less than velocity at 1 point, it means at which point let's say upstream velocity is 10 meter per second, and here at 1 millimeter distance from the surface, 1 millimeter, here velocity is u1, u2 is more than u1. So at which point the fluid has to be, at which point the delta will be higher. Delta means, what delta is there? Delta is the thickness in the y direction where the fluid velocity is 99% of upstream velocity. Means at which point the fluid will acquire the velocity close to the upstream velocity or free stream velocity. Tell me. At which point the fluid will require more y, more delta to cover the same drop? At 2 point? Yes or no? So in order to attain the same change in the velocity, the fluid at point 2 will have to cover the more distance in the y. Yes or no? And that's why the thickness grows, because with increasing distance from the leading edge means here x here, the effect of viscosity penetrates further into the free stream. The viscosity, due to viscosity, effect of viscosity causes the, why I am saying viscosity effect? Because due to viscosity only the velocity of the fluid get decreases, velocity of the fluid get changes. Is this clear? So at which point the gradient will be higher? At 1 point and 2 point. If you are talking about the velocity gradient, which point will be higher? Because if you see, my dear student, here the velocity at y equal to 0 and here velocity is less, then obviously the same distance is there, the du upon dy is a gradient. Du upon dy is gradient. So y is same here, du is less in the second point as compared to the first point. Yes or no? So can you say कि du upon dy at the second point is less than du upon dy at the first point? at wall, at y equal to 0, at y equal to 0 at one point. बोलो. So if you draw the profile, my dear student, then here listen carefully. Your velocity should be at, sorry, velocity at this point should be like this. Here it should be less. This is much more wider, this is less wider. This is what the change in the velocity profile. Is this clear? At any common distance in the y, the velocity will be higher and lower in the second point. Is this clear? Bolo beta. And if you draw the tangent at the wall means y equal to 0. This and this. Obviously, the much more gradient. This slope is more. Theta 2 and theta 1. My dear student, if you see, is much more narrower, is much more wider. Is clear? So theta 1 is less than theta 2. Is this clear, beta? And theta 2 is where theta is. Where what theta? Theta is not the gradient. Is this dy upon du? It's y axis. It's u axis. So it's dy upon du. And that's why I told you, since theta 2 is more than theta 1, that's why gradient it will be inverse. Clear, beta? Bolo. So gradient at the wall is going to be decreases, although the angle will get here if you draw tangent and here if you draw tangent. So this theta 1 and this is theta 2. Theta 2 is more than theta 1. Is this clear? Because theta is not the gradient. Theta is inverse of gradient. Yes or no? And as the velocity gradient get decreases, the thickness velocity gradient get decreases means the same velocity you will achieve by gradient decrease कर गया. इसका मतलब क्या हो गया भाई? If du upon dy get decreases, what does it means here? It means the same velocity you will get in higher distance. That is what meaning. Same difference in the velocity you will get in the larger distance. Yes or no? Du upon dy, it means delta u upon delta y, you can say, and delta close to delta u, nothing, it's u infinite minus 0, and this is nothing, it's delta minus 0. So what I am saying to you, ki as my dear student, as the gradient decreases, the u infinite is same here, delta has to be increased. So as du upon dy at the wall at y equal to 0 decreases, this implies u infinite upon delta also get decreases, and since u infinite is constant, this implies delta has to be increased. That's what the meaning, and that's why thickness grade increases, and this is called as age, where the velocity is 99% of upstream. Here only at a small distance upstream, means at point 1 only this much distance the velocity will reach to 99%, but in the delta at second point the velocity more y is required to reach the velocity to reach the 99% upstream. Is this clear? Reason is clear? Bolo beta. This is what the fluid mechanics, and why the fluid mechanics is important in the study of convection, because I told you the convection heat transfer is strongly influenced by the flow field. That's why we should know the flow property and flow velocity profile. Is this clear? So you can see this is what the flow over the flat plate can be divided in two regions. Flow over a flat plate divide into two regions. One is called boundary layer region, other is outside the boundary layer region. Yes or no? In this boundary region, gradient exist. Gradient and shear stress will exist. Yes or no? Or gradient and shear stress are large. Gradient and shear stress are large. And in that outside, what happened? What about outside boundary region? What about outside the boundary region? Gradient and shear stress are zero or negligible. Either zero or they are negligible. Are either zero or negligible. Clear? Any problem? And this line is called edge of boundary layer, that I'm going to highlight here. This is called edge of boundary layer. Edge of boundary layer. This edge will demarcate the region of boundary layer with the outside boundary layer region. And outside boundary also called a potential flow region. Also called as potential flow region. Potential flow region. Is this clear, beta? No stress is there. And this edge is an imaginary line that demarcate the boundary layer region with the outside the boundary layer region. Is this clear? Miss, this line will simply demarcate कि outside that line the flow is uniform and there is no stress or negligible stress is there, and within that line there is a boundary layer region. Is this clear? Bolo. My dear student, listen, as I told you कि as the stress is proportional to gradient and each and every point in the y, you can see if you draw the profile. Let's say this is our profile is there. At each and every point you have seen the gradient is going to change. By यहाँ पे different gradient is there, here different gradient is there, here different gradient is there. It means slope is going to change, yes or no? Tell me please. At every point the gradient is going to change here, at y equal delta, the gradient becomes 0. So you can see, can you write here, because this slope is theta, and inverse of theta is what? Inverse of theta is called as beta. It's a 1 point, is 2 point, 3 point, is called as gradient. Be careful. So at y more than or equal to delta, the du upon dy is equal to 0, or theta is infinite. And from y equal to 0 to delta, the gradient is there. Du upon dy is non-zero. Yes or no? And that is called as boundary layer region. From y more than 0 to less than delta or equal to delta. Boundary layer region. Yes or no, beta? And also you can write here, these are the bound at y equal to delta, u is equal to what? Infinite, u infinite, close to u infinite. Today I will complete the velocity boundary layer. All topics about the boundary layer, velocity boundary. Now is this clear? Now one more thing here, my dear student. As I told you, if you want to find out from Newton's law of viscosity, from Newton's law of viscosity, tau is equal to mu into du upon dy. And since du upon dy is going to vary from 0 delta, that's why for wall shear stress is tau s, s means surface of wall, is equal to mu into du upon dy at y equal to 0. Bolo. By at the wall, we should write the gradient at the wall, means at y equal to 0. And since du upon dy at y equal to 0, which is velocity gradient at the wall, which is velocity gradient at the wall, is a function of x. Yes or no? Because as x will change from 1 point to 2 point, the I told you na, slope will change, then gradient will change. Yes or no? By du upon velocity gradient at the wall is a function, I told you na, theta 1, theta 2, you can see they are the slope at the wall, and theta 2 is more than theta 1. That's why the gradient of the velocity is at the 1 point is more than the 2 point. So gradient is going to change here. Then since velocity gradient is a function of x, then tau will also function of x. Hence tau s is also function of x. Yes or no? So surface shear stress or surface momentum flux is also function of x. Clear? So what I want to discuss here, my dear student, to find the shear stress at any x, we must know velocity gradient at all x at the wall. In order to find Pucha 10 minutes. Give me water please, if you are comfortable to give. In order to find shear wall shear, a surface shear stress distribution, surface shear stress means tau s at any x, we must know, we must have information about what, gradient at that x, surface gradient, surface velocity gradient means du upon dy at y equal to 0 means surface at that x, and which is very difficult. Yes or no? How can find the velocity gradient at all x? So from this definition, listen, very important, from definition from equation 1, to find out shear stress at any given x, we must know velocity gradient at all x, at that x. So there is an alternate approach. There is an alternate, because that you can only find out if you know the velocity profile. If you don't know the velocity profile, you can't find out the shear stress at the surface at different x. Yes or no? There is an alternate approach to find surface shear stress or wall shear stress without velocity distribution, without knowing velocity distribution. देखो बेटा, if velocity distribution known to you means u is a function of y is known to you, तो क्या करोगे आप? You should only differentiate with respect to y at y equal to, put y equal to 0 and you can find the gradient, है ना? But this velocity profile is not the constant, it is going to vary from one x to other x. So this u is a function of x and y. So what you should do, the x at which you want to find out the x at which you want to find out the gradient, you should put differentiate and put y equal to 0, and put in this equation you can find the shear stress at that x. It is clear? And shear stress is nothing, it's a momentum flux at that x. It is clear? But there is an alternate approach to find out the surface shear stress without knowing the distribution. That is what? Skin friction coefficient, and that is what? CFX. Friction coefficient is tau surface x upon half rho u infinity square. That is the formula, where CF is called as skin friction coefficient. Have you heard about this? Means by using the skin friction coefficient, we can find the shear stress at any given x. That's it. Yes or no, beta? It is second equation. The first equation that required the velocity distribution at all x at y equal to 0. But here we can also find out the same shear stress distribution without knowing the velocity distribution, by knowing only CFX, skin friction coefficient. It is clear, and that is most widely used. This equation 1, you can only use to find out the shear stress when the velocity distribution is known to you. क्लियर है बेटा? बोलो. This is all about your velocity boundary layer. Any problem till now? Tell me. So please, you should anyone should recall me by tomorrow. I will send you the assignments question based on the. Already I told you the sources, but still I can send you some more questions from on the conduction. है ना? Already I send you. Fins के question solve हो गए? What I send you in the group? बोलो. So these topics are clear, yes or no? Do you got some clarity about this? Chiru, I'm asking to everyone. Thank you so much. We'll meet tomorrow at the same time. Few days I will take classes in the evening only.